So welcome everyone. Thank you very much for joining. This is our 13th webinar within this ECE Data Science Distinguished Series. I hope that you all had a great first month of this unusual semester. Before presenting our speaker today, let me briefly go over some logistics. If you have any questions, you can write them in the Q&A chat, and towards the end of the talk, we're going to select some of those to be answered by our speaker. During the talk, I'll also monitor the Q&A in case there's any pressing clarification question that makes sense to address in the middle of the talk. Otherwise, we're going to address most of the questions towards the end. The talk will also be recorded and uploaded to our YouTube channel for future access. That being said, it is my pleasure to present today Professor Olgica Milenkovic as our distinguished speaker for the data science seminar. Professor Milenkovic obtained her master's degree in mathematics in 2001 and PhD in EE in 2002, both from University of Michigan. At that point, she joined the University of Colorado Boulder as an assistant professor, and later in 2007, she moved to UIUC, where she's currently a full professor of ECE and a research professor at the Coordinated Science Laboratory. Professor Milenkovic heads a group focused on addressing unique interdisciplinary research challenges, spanning areas like algorithm design and computing, bioinformatics, coding theory, machine learning, and signal processing. She has received a number of awards, including an NSF Career, the DARPA Young Faculty Award, the Dean's Excellence in Research Award, and several Best Paper Awards. In 2013, she was elected a UIUC Center for Advanced Study Associate and Willett Scholar. She's an IEEE Fellow and served as an AE in multiple IEEE journals such as Transactional Communication, Signal Processing, Information Theory, and Molecular, Biological, and Multiscale Communications, which is yet another indication of the breadth of work in Olgica's group. Personally, I met Olgica when she gave a seminar at UPenn when I was a student there. I don't know if you remember this.
Yeah, I'm nodding my head. Of course I do.
It was probably around, I was trying to remember, probably around 2013 or so. But I got the chance to discuss a bit the problem that I was working on back then, which was an axiomatic view on clustering, which kind of resonated because you were working on an axiomatic approach to constructing distances for rank comparison. So I remember that discussion. So in any case, Olgica has worked on plenty of cool graph-related problems. So I have been following her work, of course, ever since, all the way from clustering, network models, graph covering problems, and including now some more modern topics like GAN-based graph generative models. And of course, she has worked on hypergraphs, and she'll be delighting us with a talk on that topic today. So Hurricane Laura kept us from enjoying this around a month ago. So Olgica, thank you very much for your kind disposition in rescheduling. We are very happy to have you here, and the floor is all yours.
Thank you so much, Santiago, and thank you for the kindest introduction I ever heard. And it's great to be here, even after Laura. Hopefully, I heard Laura didn't create much damage. So I know it's 4 p.m. I double checked that we're in the same time zone. So a lot of you may be already ready to call the day, but I will try to go gently with the introduction of a subject that has a lot of different words in the title that may be foreign to some of you: submodular hypergraph partitioning. But I will, as I mentioned, try to present the simplest introduction to this topic. And this is something that I've been working with for a long time with my former student, Pan Lee. And Pan Lee, after graduating, took a position at Stanford University in the group of Leskovec. And he was lucky enough to join Purdue Computer Science this semester when everything is done in under special circumstances. And I hope he's surviving the teaching load and everything as well as possible. So, and thank you, Santiago, again, and thank you all for being here. So without too many delays, let me just start with the main topic of this work. And that is hypergraph and graph partitioning. So what is really graph partitioning? Let's first start discussing the notion of a graph. A graph or a network is something that we use quite often in mathematics, and we use it in data science, in machine learning. And it's a mathematical model that captures nothing more than what we call pairwise interactions. And when you have pairwise interactions, you really envision pictures like this, where you have vertices and you have links between the vertices. And there are many, many questions that you can ask once you capture these pairwise interactions, or these links that represent pairwise interactions in social networks or publication networks or nearest neighbor networks. And some of the questions that are really practically useful is, how can you perform graph partitioning? And usually when we say graph partitioning, we mean vertex partitioning. So you want to partition the set of vertices according to some criteria, and the criteria you use is really governed by the application. You can think of graph clustering or community detection. There are applications in circuit design, image segmentation, and the list is really endless. I will touch upon a few of these topics later on in my talk, but you can imagine once you're given a graph, you can ask for a large number of problems that you want to solve on the graph. And a lot of them are important in classical mathematics, but also in machine learning. And when you are particularly interested in this problem of graph partitioning, or partitioning the set of vertices according to some criteria, then you have occasionally constraints that you have to respect. Basically, how many parts or clusters do you want to have or allow? Do these parts have to have some size constraint? Are the graphs parts going to be balanced in size? Are they going to allow to are we going to allow them to overlap, and so on? So more formally or more mathematically, the setup for graph partitioning is as follows. You have a graph which we will describe in terms of the vertex sets, these blue circles here, edges, which are the pairwise links, and weights, WE, which we will assume to be positive. And these weights, WE, are associated with edges. So think of every edge having a non-negative weight associated with it. And then the partition function that we use, or partition objective function, may be defined in terms of both the topology of the graph, basically the links you see here, or the edge weights of the graph. And the task that we are interested in is to optimize this partition objective function, and either minimize or maximize depending on what we are interested in solving. So if you, oops, sorry, I'm going the wrong direction. So one interesting partitioning approach is what we call agnostic graph partitioning. And this is a work that originated in the theoretical computer science community. Bansal, Bloom, and Chawla in 2004 asked the question, if you can partition a graph without knowing the number of parts that will give you the optimal partition. And this is agnostic clustering or partitioning, because we do not know in advance how many parts are optimal in the solution. So for example, you can ask to maximize the agreement. This is a form of correlation clustering, where you're asked to basically maximize the sum of the weights of edges within clusters and the sum of certain edges that go across clusters, or to minimize disagreement, which is going in the opposite way. And here is a simple example. If you are clustering this particular graph with these weights here, you would like to have and learn that there are going to be three clusters. These two vertices lie in one cluster, these two vertices lie in one cluster, this vertex lies in a separate cluster. Your objective was to optimize the number of blue edges within cluster and the number of orange edges across clusters, and you didn't know what would be the optimum number of clusters for this problem. It's something you learn as part of your optimization procedure. And this is what we call agnostic graph partitioning or correlation clustering. On the other hand, something that you may be much more aware is not exactly this combinatorial approach that asks you to simultaneously find the number of clusters, as well as, or parts, as well as the distribution of vertices into the different parts, but also something that has broader applications and is easier to do computationally, and that is really this notion of spectral graph partitioning. And in this setup, you again have a graph which is defined in terms of a vertex set, an edge set, and weights. And for simplicity, we will only consider partitioning tasks when you have two sets. So you want to partition the vertices into two sets, S and S bar. And the goal and the question of this partitioning method is to partition the set V so as to minimize the boundary of a set S. And what is the boundary? The boundary of a set S of vertices, a subset of the vertices, is the collection of all edges such that the edge has one endpoint in S and another endpoint in S complement. So if you think about this example here, the boundary would be between the set A and the set B will be the set of these two edges because they go across from A to B. So one endpoint is in A, the other one is in B. And we are saying that an edge is cut by this partition if it belongs to the boundary. So this is the terminology and notation. And the total cut cost, a definition that is very relevant for the subsequent discussion, the total cut cost between these two parts of the graph, this is part A, this is part B, would be the sum of the weights of the edges that are in the boundary, that basically have one vertex in A and another vertex in B. So once we have a definition of a cut, we also need to introduce a definition of the volume of the set. And the volume of the set S is defined as nothing more as the sum of the degrees of the vertices in the set. And here the degrees are weighted degrees because we are working with weighted graphs. And with these notations in mind, we can define the objective that we are after in this graph partitioning approach, which I'm discussing under the name of spectral graph partitioning. The objective will be the cut of S divided by the minimum of the volume of the set S and its complement. And this is what we call the conductance of the set S. And why conductance? Because of practical reasons. Sets that have small conductance really have been shown to correspond to high quality clusters. So if your goal is to do partitioning for the purpose of clustering, and you want to do community detection and clustering on real networks, then it really makes sense to use small conductance, as a criteria for the goodness of your clustering. And this work here by the Leskovitz group really provides an interesting study on real data sets that shows that small conductance leads to good clusterings. And then our optimization problem will obviously read as follows. You want to find a set S that minimize this psi of S, which is the conductance, cut of S divided by the volume of S or its complement, whichever is smaller. So this is a difficult optimization problem. And we cannot really solve it directly, but we use approximate solvers. And the method of choice that has received incredible attention in the past is this so-called spectral clustering method that pretty much everyone of you has heard about. There is a very nice introductory exposition of spectral clustering from 2007, and if you ever worked in spectral clustering, you know that these three lines summarize all you need to know about how the algorithm works. You have an adjacency matrix of a graph, and an adjacency matrix of the graph will just tell you which of the vertices are connected by an edge, but you clearly have the weights of the edges that you have to work with. And you have a diagonal degree matrix, a matrix that has the weighted degrees on its diagonal. What you first do in these computations is to evaluate or find the symmetric normalized Laplacian. So this Laplacian is really a matrix that you obtain by scaling your adjacency matrix by the degree matrices, square roots of the degree matrices, and subtracting them from the identity matrix I. You find the Laplacian, and then you compute the eigenvector B that is associated with the second smallest eigenvalue of the Laplacian. And then you partition the set of vertices according to the value of this second smallest eigenvector scaled by square root of D. And this is a old approach that has been studied and analyzed and used in many, many practical applications. And the reason why we are sticking with Laplacians is for the simple reasons that we can describe very interesting quadratic forms that involve the Laplacians. So very simple algebra will tell you that if you take the Laplacian of a matrix and some vector x in Rn, and you compute this product here, you will get a quadratic form of this type. That's a very easy algebraic manipulation of the definition of a Laplacian. And then the interesting observation is that if you take specific values for the entries of the vector x based on your u being in the set, a vertex u being in the set S or not being in the set S, and that value is equal to plus minus and then a ratio of the volumes of the set and its complement, but one is in the numerator and the other one is the denominator. If you replace these values into the quadratic form above, first you will see that this xt Laplacian x is proportional to the conductance, and the scaling factor is just the volume of the vertex set. And hence minimizing this conductance is equivalent to minimizing this quadratic form, but conditioned on x being of this form and dx being normal orthogonal to 1, and this additional constraint that it comes up from simple analysis of the formula being true. So obviously, if you now have this quadratic form and you work in signal processing or in spectral graph theory, you know immediately what's next. What's next is to dispose of the constraint that xu has to be in this form, and then just solve the relaxed problem where xu is allowed to be anything. And in this case, you still use the conditions that you had before, but now your x is unconstrained. You have a relaxed problem, and that relaxed problem ties up nicely with the definition of the classical Rayleigh quotient you use when you try to explain how to compute eigenvalues. So this really brings into the picture spectral graph theory, and this is how the connection comes about, because spectral graph theory is the means of all these partitioning, is the enabler of all these partitioning algorithms that you see in practice, like the one that I had just explained. So if size the conductance obtained via spectral graph clustering, and the optimal conductance, which we call the Cheeger constant, is denoted by psi star, then a very beautiful result that dates back to 97 by Fan Chang basically establishes that spectral graph clustering, when it comes to the goal of partitioning a graph, will be quadratically optimal, because you can bound the conductance obtained from the spectral graph clustering algorithm only in terms of a square root of the optimal conductance, or vice versa. So a direct consequence of this Cheeger's inequality, it's just the way you interpret this result, is that if lambda is the second smallest eigenvalue of the Laplacian, then you have this sandwich inequality that holds true for the second smallest eigenvalue in terms of the optimal conductance, or the Cheeger constant. So this was really a crash course on spectral partitioning and spectral graph partitioning for those of you that may not have seen this topic before. And it's really something that I had to cover before I give you a much more interesting flavor of how to do spectral partitioning on objects that are not exactly graphs, but something that can capture higher order relationships. And this brings me really to the topic of hypergraph partitioning. And this is where I will slow down and introduce some interesting applications of the problem, and explain why do we really need to move on from the well-studied subject of graph partitioning to the significantly less studied problem of hypergraph partitioning. So graphs, as I explained already, model pairwise relations. But higher order relations are much more interesting. These are relations that involve more than two entities. And higher order relations are usually described with what we call hypergraphs. So hypergraphs include or involve hyperedges that comprise more than two, usually comprise more than two vertices. In the literature, a lot of the community members from the KDD community or from data mining in general will use the notion of a motif, or the name motif rather than a hyperedge, but a motif and a hyperedge can be understood to be the same object. So here is an example, and I apologize, I shouldn't have called this a simple graph. This is just the graph, an ordinary graph. And you see that in an ordinary graph, the links that we draw really capture pairwise relations. They tell you, for example, if V1 and V3 are friends in a social network. Well, if we move to a hypergraph, then we are capturing relationships between more than two vertices. We can still have relationships that correspond to two vertices. This would be just what we call a hyperedge with two vertices, but we are allowed to involve more than two vertices in a hyperedge. So in this case, this will be what we call a hypergraph. This will be one hyperedge that involves three vertices. This will be another hyperedge that involves two vertices, while this will be a third hyperedge that involves four vertices. And we can discuss incidence matrices of these hypergraphs and other subjects, but it's pretty obvious how to extend everything in terms of a definition of a graph to a hypergraph, and that is what we will skip just for the sake of time. So where do hypergraphs arise in practice? And the answer is pretty much everywhere. So hypergraphs are actually much more present in real life than graphs, because they arise in biology a lot, they arise in social networks. So here are two examples. This is a list of so-called motifs in social and biological networks. And in particular, this is from a book by Uri Alon from 2002, describing different types of higher order interactions in biological networks. And the same higher order interactions are present, or a lot of the same higher order interactions are present in social networks. So we know that we have something called a feedback loop, which serves as a delay unit in biological networks. And this feedback loop involves usually three entities. And on top of it, you have directions, not just ordinary graphs, but or hypergraphs, but directed hypergraphs, where you can think of there being some direction with which the vertices interact with each other. Another example where you will see hypergraphs is hierarchical food chain networks, like these here that were studied by Urbana Zeleskovic's group and published in a science paper from 2016. Other applications, for those of you that are interested in information networks, citation networks, hyperedges really appear in these type of analysis. Jiawei Han works a lot with these types of networks, where you are really dealing with hyperedges that capture metagraphs and metapaths in heterogeneous information networks. So what you have in a nutshell here is you have hyperedges that involve multiple vertices, and the vertices have different labels. So for example, if you have a paper, the vertices may correspond to the title of the paper, the venue at which the paper was published, the author list, and all these vertices together give you one hyperedge that corresponds to that paper. They have been used quite a lot. Hypergraphs have been used quite a lot in VLSI circuit design, and there were a lot of heuristic algorithms. And I emphasize heuristic algorithms because the theory or the analysis behind hypergraph learning problems came only about in the last 5-6 years or so. So in VLSI circuit design, you can look at some components of the circuits as entities that have to be optimized together, and these obviously correspond to hyperedges. In computer vision, again, hyperedges arise because segments of the image can be collections of pixels of an image can be lumped together to form one hyperedge, and then clearly you can phrase a lot of the questions that you have in image partitioning or segmentation, image segmentation, using the concept of hypergraph partitioning that I will cover in a second. So hypergraph partitioning, again, comes in two flavors. It's the same kind of outline that I had for graph partitioning. You can do it in an agnostic way, and in that case, it's called hypergraph correlation clustering or motif correlation clustering. And just for the sake of time, I'll skip this, but you can read more about the agnostic version of partitioning of a hypergraph in the papers described here that come from my group from 15, 16, and 20. And basically, just as a really brief outline, if you split, if you place a hyperedge across the vertices of a hyperedge across two different clusters, you are penalized with a certain cost or weight. But if you place a hyperedge in all within a single cluster or single part, meaning all the vertices of the hyperedge end up in one cluster, in one part or one cluster, then you have a different penalty. And your goal would be basically to optimize the objective cost, which tells you something about how many of the costly clusters or costly hypergraphs did you put within the same cluster or across cluster. Or in a more interesting formulation that is due to also the Leskovic group in a paper that I mentioned from 2016, you can basically ask about the hypergraph or motif partitioning problem in the same manner that we discussed the graph partitioning problem in the spectral graph partitioning or clustering framework. And this in this framework, again, we assume that we have a set of vertices and then a set of hyperedges. So all we have to know is that the collection of vertices within the edges can be larger than or equal to 2 in size. And each of the hyperedges also comes with a weight. And you determine what your favorite hyperedge is, or your favorite motif, basically a subgraph in the network. And then you can define what is called a hyperedge or motif-based conductance as follows. If you are going to partition the set of hyperedges or vertices in such a way that you minimize the number of hyperedges that go, or interesting or relevant hyperedges that go across clusters, then you would do a similar, you would have a similar definition for the conductance of a motif or a hyperedge or a subgraph. And in this case, what you see basically is that this 3 hyperedge or 3 vertex motif has the property that 1 vertex lies in S and 2 vertices lie in S prime. If this motif comes with the weight, you will be charged the weight of this motif to place it across clusters or across parts. If you have, for example, this interesting motif here, it's all within a same cluster or the same part S, then you would pay a different cost. And clearly, if you don't have costs and all the weights or costs are 1, then you would only count how many of your useful or interesting hyperedges are being cut by this partition, and that will give rise to the same or a similar type of notion that we call conductance for graphs. And you will define the conductance as the number of motifs cut divided by the motif volume. So if you do this, if you want to analyze this motif-based or hypergraph-based conductance, you run into a lot of trouble because unlike the nice case for graph partitioning where we had a Laplacian to work with, and that's why I spend a little bit more time discussing a Laplacian, there is no matrix form for the Laplacian of a hypergraph. What comes to your mind immediately is why not work with tensors or some other type of objects, the problems are become really hard. So working with matrix forms for hypergraph Laplacians is impossible because such matrix forms really don't exist. So what you can do instead is to forget about matrix forms that operate directly on hypergraphs, but instead use what we would call a matrix approximation for the Laplacian. And that is an idea that goes back to Zhou and his collaborators from a 2007 NIPS paper. And it is well known in the community under the name of a projection method. And the idea is you project, quote unquote, a hypergraph into a graph, and then you apply a standard spectral graph clustering procedure. This is a very efficient procedure, but it introduces what we call a large distortion, because when you try to represent higher order relations in terms of pairwise relations, you're really introducing or losing information, and you're introducing errors in the way you describe the model. And you defeat the purpose of trying to basically look at the model as a model that captures higher order interactions. So there is a second way to go about and use nonlinear Laplacians. And this is an area that is highly mathematical and very complicated to describe in a short time. So I suggest to the interested observers here to check out a bunch of papers that Pan Li and I wrote in 17, 18, and 20, and there's really interesting work by Yoshida from the 2020 and from some previous years as well. The problem with these nonlinear Laplacian spectrum approximations is the fact that the distortion can be kept at bay. So you're really working with higher order relations, but the algorithms that will help you do partitioning and multi-way partitioning become really complex. And we don't know at this point if the complexity of these algorithms can be really reduced to the point that we can practically apply these algorithms. So what I'm going to do today in the remainder of the time that I have is to discuss these matrix approximation algorithms for the Laplacians, basically the projection method, and then describe why the projection method by itself is not going to work for all choices of weights and all problems of interest in hypergraph partitioning. So let's look at what the projection method really does. So as an example, let's use a hypergraph that has an arbitrary sized set of hyperedges. And let's look at how this projection method works on an arbitrary hypergraph. What you do is you basically take every hyperedge and you create a weighted clique for that hyperedge. So basically, if you have 4 vertices in an hyperedge, you will create a clique of size 4. And what is usually the practice is to take the weight of the hyperedge itself, the weight that describes the penalty you pay when you split the hyperedge. And what is commonly done, this weight of a hyperedge is split equally among all the edges that you have in the clique. So then when you do these projections onto cliques, you just merge the edges, multi-edges that may arise in this process, because the same pair of vertices may lie in multiple hyperedges. So there will be multiple edges connecting the same pair of vertices. You will sum up their weights, and that is what we call merger. And then you will use this graph that you obtain through the projection method, and you run your classical spectral graph clustering on this graph using the Laplacian that I described in the first few slides. So as an example here, here is how this projection method would work on a 3 regular constant weight 3 hypergraph. So here, all the blue shaded regions really represent hyperedges, and you can view them also as triangles that would give rise to the name motif. Motif triangle motif, but these are also hyperedges. So what you do is you take all of these triangles that are present in this graph, and then you project them. In this case, you're really not doing anything specific, anything different than creating another triangle from this triangle, but the weights on the edges will change, and they will become WE over E, in this case WE over 3. So if you have larger hyperedges, then you will get larger cliques here, not just triangle, but a 4-clique or a 5-clique. And then in the step of merging, I would look at every double-edged formed or triple-edged form and sum up the weights that I assigned for to each of these projected edges, and I will get in this process something that I call a weight merged graph. And this is nothing more than a simple projection, or what we call a projection of the hypergraph into a weighted graph where the weights are really obtained by simply splitting the weight of the underlying hyperedge. And clearly here, because I have this pair of vertices participating in this hyperedge and in this hyperedge, I have weight 2, a contribution 2, while, for example, this pair of vertices only jointly participated in one hyperedge, I have weight 1 here. So after I am done with this projection step, I will just run spectral graph clustering, and that result will tell me how to partition the vertices of this graph while trying to basically optimize a proxy for the conductance that I had before. So unfortunately, this projection method can be easily seen to cause what we call huge distortions. And the issue can be easily understood without any mathematical analysis from the following observation. Let's assume that we had this hyperedge here that involves 6 vertices. When I do clique projection, I will get a clique of size 6 that represents this hyperedge. And since I'm splitting the weights uniformly, every one of these links will basically get the same weight inherited from this hyperedge. And that is obviously not something that is a good idea, because now if I do a partitioning of this set of vertices here in such a way that this vertex lies in one part and the remaining vertices lie in another part, then this cut will be roughly proportional to the size of the hyperedge. This is going to be exactly E minus 1, where E is bar E is the size of the hyperedge. And clearly, this will have the same cost in the spectral graph clustering approach as this here, where I am running a partition which involves 3 vertices here and 3 vertices here, which obviously involves cutting E squared edges in the projected domain. So you cannot reconcile these two, because these two are basically a factor of E away, and both of them are going to be treated the same way by the spectral clustering algorithm. And this is what we call distortion, because we cannot control this case. So this gets even worse if you don't have the same weights for all the cuts. This is assuming that the weight WE associated with the hyperedge is such that you use only one weight. If you cut the hyperedge, you are charged that weight WE. If you don't cut the hyperedge, you are not charged that weight. So this gives me gets me to the topic that I was planning to discuss from the first slide on, and this is what we call submodular hypergraph partitioning. So it's a way to figure out basically when will these projection methods work, what kind of weights will allow us to make this distortion be controlled, and it will also tell us how these hypergraph partitioning algorithms can be made to work on a much larger set of problems. So first of all, as I mentioned already, when we deal with classical hypergraph partitioning, we have several drawbacks. The drawbacks that I will discuss in this slide are the fact that they don't account for heterogeneous vertices. If you work in biology, neuroscience, social networks, and if you remember the example where I mentioned that the vertices in a hyperedge that corresponds to, for example, a paper can be authors, can be titles, can be publication venues, then you know that not all vertices are of the same type. So for example, in metabolic networks, you can have vertices that are metabolites like B and C, and vertices that are products of the metabolic relation. And then clearly you would like to know, should I really charge the same cost or have the same weight of splitting this triple of vertices according to this partition, A in one part, B and C in another, versus placing A and C in one part versus B in another part. So you have a bunch of other examples where you can see that it makes sense, for example, in this case, to keep B and C in one part and A in another part, versus having this kind of cut which will lump A and C together. So we shouldn't treat all cuts or all partitions of a group of heterogeneous vertices in the same way. So this is one question that we didn't resolve with the classical hypergraph partitioning problem, the fact that vertices can be highly heterogeneous, and we shouldn't be basically having the same cost for each cut, independent on which vertices are in S versus S complement. And the second thing is obviously this notion of distortion that I described, which we couldn't really resolve well because we knew from this example that we can have a distortion that is as large as the largest hyperedge that we have in the hypergraph. So how can we really address these two questions in one framework? And the answer to this question is to introduce what we call inhomogeneous or non-uniform costs for splitting or partitioning in hyperedge or cutting in hyperedge. And to control the large distortion, the even larger distortion that would come about in this context, we will try to figure out when can this distortion be controlled, what are the conditions on the weights that we allow that will make these projections have controlled distortions. And this is where the notion of submodular weights will come into the picture. So going from hypergraphs to inhomogeneous hypergraphs, as we call them, all we're going to do is to assume that the weights we have that we use for each of the hyperedge will now come in the form of vectors. So we no longer have one weight, but we have a vector of weights associated with each hyperedge, which tells us how much does a particular subset S of the vertices in the hyperedge contribute to this higher order relation E. So this WES will be the weight that you assign to a split of the hyperedge, which has a subset S of the vertices in the hyperedge E on one side and the E minus S on the other side. And this is basically what measures the contribution of this subset of S vertices in the hyperedge towards the higher order relation that E, the hyperedge, is supposed to capture. We have a small symmetry condition here, and that is that the weight of a subset of vertices in the hyperedge should be the same as the weight of the complement with respect to the vertex set of the hyperedge. And for each of these, we will have separate numbers that are not non-negative numbers. And graphs which have weights, hypergraphs that have weights of this form associated with each of the hyperedges we will call inhomogeneous hypergraphs. Clearly, if the weights are the same, independent on how we choose the subset of the vertices in the hyperedge, then we go back to the original hypergraph clustering problem. This is when WS is constant, so we just have one value, not a vector of values. And for example, in this case, if I place A in one cluster and B and C in another cluster, I will pay the same cost, or I will be charged the same way, WE. If I do the same thing with B versus AC, I will still be paying the same price. But here, clearly, if I place A in one cluster and B and C in another cluster, I pay one weight, which I called weight of A. If I place B in one part or cluster and the other two vertices in another cluster, I paid a different weight, which I call weight B, and so on. So the idea should be clear. So this is what we call inhomogeneous clustering. So what has to change in the definitions of the cuts? All we have to do is just make sure that we understand that now if we have a set S, then we have to basically see how that set S intersects a hyperedge. Basically, what this says is we need to see which of the vertices of E lie in one part of the cut, which vertices of E lie in another part. So this is how we would look at the boundary, and the cut will be the sum of all these vertices. Of all the sets that are or subsets that are of E that belong to one part and another part. So the definition should be clean based on what I just described on the previous example. The volume of the set will still be the weight of the sum of the weighted degrees, but the weighted degrees now will be the weights of the singletons. Where V singletons V, where V is the actual vertex whose degree we are interested in. And the objective then can be defined in exactly the same way as the cut of S divided by the max of the volumes of the two parts of the cut. So now the key question is really, can we do a projection of these inhomogeneous hyperedges into cliques to achieve a good approximation of the costs of or the cuts that we have in the hypergraph domain when looking at the solution in the graph domain. Or more precisely, if we are going to look at the cost of the cut that involves a subset S of the vertices of an edge E, can we project the weights or the hyperedge weights that we have into edge weights, so that the total sum of these weights when we perform the merging procedure, which is captured by this sum here, is really a good proxy for the original weight of the split of the hyperedge into weight of S and weight of S, E minus S, which is the same. So we're looking for some constant beta that will allow me to sandwich the merged weight in terms of the original weight and a scalar that doesn't depend on the size of the hypergraph. On the right-hand side, there is a multiplier of the weight of S. So since I'm running out of time, I just want to give you the main idea. When is a solution to this optimization problem possible, and why is it possible? In a nutshell, the solutions to this problem may not be even feasible. And we know of a bunch of examples when that is the case. If it were feasible, we could establish some analogs of this Cheeger inequality that I discussed before. But the challenges are that we basically don't know when such feasible solutions exist. And even worse, we may end up having weights that are generated as solutions of this optimization problem that are negative, which is not something we allow. So the idea is to observe that we are trying to approximate a cut function, because when we're trying to do the partitioning of hypergraphs, we're really trying to approximate in this formula here a cut function. And a graph cut is what we call a submodular function. So a graph cut is a submodular function, and but a definition of a submodular function is very straightforward. I'm assuming that a lot of you have seen this before. So we call a function submodular if it has what we call diminishing returns. If you take two sets, one of which is S1, a subset of S2, and you take a vertex V, which is not in S2, and you augment the smaller set by V and check the difference in the weights of the augmented set and the original set, that difference is greater than or equal than the difference that you get when augmenting the larger of the two sets by V. That is what we call a submodular function. And we will introduce this notion of submodular weights as weights that have the submodularity property. And when weights are submodular, when these weights that we assign to different cuts of the hyperedges are submodular, then intuitively you should believe that I have a cut function, a submodular function, that I'm trying to approximate by using a graph cut, the projected graph cut, and things should be we should be able to come up with a good approximation. And I will spare you the results because the results are a bit complicated. I will just tell you that you can find these beta parameters which tell you the distortion, and the distortion, for example, for triangles is 1, for hyperedges up to size 5 is 2, and so on, for special cases when the cut weights are submodular functions. And you can even find the min-max optimal solution in closed form, which is a complicated derivation that I will skip. So due to time limitations, I know I have only a few minutes left. I just want to show you a few applications without going into the details, and just describe to you basically what these techniques of inhomogeneous hypergraph partitioning allow you to do with real data. So for example, you can use these methods for hierarchical clustering. This is the food network that I described in one of the previous slides. And this is the test example used in Leskovic's paper. Leskovec and his group tried homogeneous hypergraph clustering on this problem. And I will skip to the results. And this is the kind of clustering they got. Almost 60–70% of the vertices were not clustered. They couldn't place the vertices in any of the clusters, and the clusters basically didn't have a nice hierarchical structure. You couldn't discern a hierarchical structure. While if you use our submodular clustering paradigm for hierarchical clustering, where you use these weights and you use 4 vertices or 4 hyperedges, you get a very pretty hierarchical clustering. Observe that in this case, when you deal with hierarchical clustering, you want to actually maximize the number of edges that go across different parts of the graph. Basically, you have a multi-part graph, and you want to have dense components between the parts and sparse connectivities within the components itself. It's something that you can easily adjust to work within our framework. So as I'm mentioning here in this set of results, when you use the inhomogeneous hypergraph clustering problem, you leave no vertex behind. You basically have only a few edges that can be attributed to clustering errors. These are I believe, 6 cases drawn in black in this hierarchical clustering diagram. You can use these inhomogeneous clustering paradigms or partitioning paradigms to learn categories in rankings. And for example, this is a famous data set from the Irish House of Parliament election from 2002. And without going into too much detail, because I really don't have a lot of time, the interesting observation here is that mutual information is a submodular function. And if you use mutual information as a weight for our partitioning procedure, then we can determine again, a hierarchy of the candidates in different parties, as illustrated in this picture, in a way that is much more efficient compared to other existing methods. Basically, you can use only 70% of the samples that were used in the state-of-the-art learning methods on rankings versus what we did, and we only needed to estimate 30% the mutual information for 3 hyperedges, and in this case, only 30% of these 3 hyperedges. You can use the same methods for subspace segmentation, and we have a nice illustration of how subspace segmentation can be formulated as a hypergraph partitioning, inhomogeneous hypergraph partitioning problem. And a very exciting application that we just got NSF funding for is to use inhomogeneous hypergraph clustering methods or partitioning methods for these so-called chromatin interaction data sets, where we are trying to determine which parts of DNA, in a nutshell and very simplified, which parts of a DNA fragment are in physical contact with each other, because DNA is not a straight line that is stretched from here to eternity. It's basically a knotted structure that resides in the cell nucleus, and as a knotted structure, different parts of the string that are physically not close to each other come in physical contact due to knotting and to folding of the structure. And these contacts involve multiple parts of the chromatin complex. And this is a very interesting new area that we are examining, because we have both heterogeneous vertices and we have multi-way interactions. And now we also have a technology of our collaborating lab that allows us to measure multi-way interactions using a technology called Chia drop. So I know I'm barely on time here and I skipped a lot of things. Hopefully the questions and answers will help with addressing it. And thank you for your attention. Sorry for bombarding you with a lot of new concepts, potentially new concepts. And if you have any questions, these are the papers that you can check out. The slides will be made available for your personal use as well if you request them. So thank you very much for your attention and for bearing with me during the last hour.
Thanks a lot, Olgica, for the presentation. I agree, a lot of information here. I think people also enjoyed it as much as I did. So we have, so remember that you can write your questions here for us to address Professor Milenkovic. So here we have the first one. So I'll just read it out for you if you want. Subtik asks, so thanks, first he said, thanks for the talk, Dr. Milenkovic. Is there any intuition for cluster centroid or distance to cluster centroid for hypergraph clusters? If yes, can you explain with a real world example?
A cluster centroid, usually what comes to your mind when you look at when you read about a cluster centroid is k-means. So it's a different type of objective that you use. So here we are using an objective which is basically the conductance. So we are really not looking at centroids and concepts of centroids that are much more common to distance-based methods such as k-means clustering. So did we think of a notion of a cluster centroid in the context of hypergraph clustering? Not really, but maybe there is a way to connect these, because we know that there are some connections between k-means and other graph clustering or spectral clustering or general clustering algorithms.
Great. Yes, thank you. Yes, exactly right. So here you can do this even in the absence of having this embedding on any space.
Yeah,
right?
yeah.
You only need the distances, and this is
right. Right. It's a different type of clustering algorithm, so we wouldn't really think of centroids in this context.
Mm-hmm. Here we have another question. It says, so we start with a clarification. So To clarify, does submodularity always hold for hypergraphs or only for some? If it only holds for some classes of hypergraphs, is there a reasonable way to project a general hypergraph onto a submodular one?
That's a very good question, and the clarification, very well-deserved question. I should have explained this better. I was rushing through it. No, the weights are something that is given by your problem, and you determine the weights, the vector of weights. You determine it based on what do you think how your hyper edge should be split. So we identified applications where those splits are naturally the weights of WES. Those weights are submodular functions. It's not true that every hypergraph will have submodular weights. You can clearly come up with examples where the weights that I assign to WES for all S subsets of the set of vertices in a hyperedge may not be submodular at all. In that case, there's nothing we can do. We are going to pay an even larger penalty when we project, because there's really nothing we can do. But what I showed you is that in a lot of examples, practical examples, you're allowed to choose your own weights, and that was the case with the food web network. Or your weights are functions that turn out to be submodular. So a lot of the interesting problems involve having weights that are either mutual information or some other information theoretic entities that we know are submodular. Clearly, if we don't have submodular weights, we are going to have a large distortion, even larger than if we had homogeneous weights. And honestly, we didn't think what we could do to project into submodular ones. That would be something to think about, and it may be pretty complicated because I skipped the proofs. They were really complicated. They were not that easy, case-by-case analysis. So it may be difficult to do this, but the message is if you already know that the weights are in information theoretic entities that you know are submodular, or you can approximate them to be submodular functions, then this is the way to go with.
Mm-hmm. Thank you, Mitch, for the question. So actually one quick one that I think was in line with that, and here I'm putting, let's say, a practitioner's hat, if you wish. So let's say that someone wants to use something like this, but it might be more often the case where the practitioner knows, this cut, I want to make it more costly than this one, or this one, more costly than that one. But having exact weights might be a little bit too much, right? So it would be the case that if you have kind of this ordinal notion of how costly different cuts should be between them, then determining specific weights that would be good for this, is that problem trivial or easy to solve or hard to solve?
No, you're bringing up the exact thing that we used again in that food web network. Let me just go back to it. And as I mentioned, it was hard to explain the topic without doing a bit of a due review of prior work in spectral graph partitioning in general. But this is a case where we pretty much did what you explained. We only know what we would like to see in the network. We want to see a hierarchical network. Yep. And the idea was two vertices in the same category or in the same layer of this hierarchical clustering or same part should be such that they're either prey for the same type of vertices in the higher level, or they're predators that hunt the same type of food. Mm-hmm. So that is basically what gives you this assumption that if you have two vertices at one layer of this hierarchy and two vertices in another layer of this hierarchy, V1 will be preying on V3 and V4, V2 will be preying on V3 and V4. So these are the same food sources for these two vertices, and these are predators for these two vertices. This is something that we came up with by looking at the fact that the network was a network, food chain network. And then what we did is we know that these links should be stronger, which partitions, parts or splits should be more costly, which splits should be less costly, but we picked these weights completely on our own.
Right.
So these weights were not given. These were the weights we chose, knowing that what we know should be costly and what should be less costly. So we just have a relational information, as you said, and then we did 1 and 2, and we did one and some other choices which are submodular, and we already got really nice results. So you don't have to know the exact weights. As a practitioner, you would just think, I have to figure out which of these vertices will I view as hyper edges, and how will I charge, or how will I split the costs of cutting these or hyper edges in a way that I get a submodular function, a submodular weight function. So this is something that we decided and came up with by just trial and error. And no, if you take some other weights, not much will change as long as they're submodular, and as long as this weight is smaller than these 2 weights, and this weight is very small compared to the others.
Great, thanks. So we'll take one more, because I know 5:10 you'll meet in reach, but I see that people have questions. I want to let anyone answer. So this is so Madeline says, thank you for the wonderful talk. Would there be any advantage on to projecting a hypergraph onto a multi-layer graph, say to avoid the merging? Right? So you had this merging operation there, right? So,
right. Oh, that's a great question too. So a clique expansion, this projection is only one type of projection. As mentioned by Santiago and everybody else, there's so many things that you have to discuss. So I didn't discuss other projection strategies. So you have something called star projection, and I'm not a big fan of a star projection. It involves creating a bipartite graph. There is a recent line of work on something called a line graph projection. So you basically don't do a clique projection, but you project a hypergraph or and the hyperedges into what we call a line graph, where the vertices are pairs of vertices in the original graph and hyperedges that they're incident to. And then you draw another graph that connects these new artificial vertices that comprise both vertices and hyperedges from the original hypergraph. So there are a lot of other projection methods that are out there, and all of them have their advantages and drawbacks. So I didn't discuss that, but it's a great point. So you can look up star projections, line graph projections. There is a very dynamic, it's a very dynamic area, but all of them have their pros and cons. So clique projection is still by far the most frequently used method for dealing with these questions.
Awesome, great. Thank you very much, Olgica, for the presentation and for answering all these questions. And thank you everyone for attending as well. So remember that this presentation has been recorded, so it will be up in case you want to listen to it again or recommend it to your friends and colleagues. So Olgica, once more, thanks for joining. And remember that now you have a few other meetings. You follow a different Zoom link, so I think you'll be meeting Rich Baranyuk in a sec.
Yeah, thanks so much, and thank you for being here at such late time and listening to a pretty complicated set of slides. Thank you very much.
Thanks, everyone.
Yeah, bye. Bye.